What's up, YouTube? Welcome to True Fringe YouTube channel. And today I'm gonna get straight to business. Not gonna beat around the bush. Uh, we're still talking about galaxies, light years, and how we determine how far a galaxy is. People, because really I believe that the foundation, really, of everything we've been taught, this infinite galaxy, uh, it all sort of rides on this one theory, and that theory is called redshift. Redshift, and here's a quick definition. Uh, so, basically, what that means is the redshift is how science determines how far celestial objects like quasars, galaxies, um, how far they are. And so you have to ask yourself, and I think this is, um, really is not um, on the forefront of the truth community enough. This is really the foundation. This is the rock that everything is standing on, as far as space is concerned, infinite space. Now, I do want to say one thing. Um, Obviously, galaxies exist. I'm not disputing galaxies and stars. I mean, we see objects in the sky. What I'm disputing is how we know how far it is. I believe in God, Jesus Christ, and I believe that uh, whatever the objects are, they're in the firmament. Um, you know, but I do know this. I just don't believe they're millions of light years away. Just don't believe it. So let's get into it. Uh, where did this redshift theory comes from? Well, it came from a guy, an astronomer named Edwin Hubble, and I'm sure you all are familiar with Edwin Hubble. Um, he is the guy, famous astronomer. He is the basically the reason that they named the Hubble telescope after him. And I think that's probably the most important point. I'm not going to get into a full bio of the guy, because really the most important thing is he is the guy that the Hubble telescope was named after. Now, here's a picture of the Hubble telescope that's allegedly 353 miles above the Earth. Okay. Now here's a quick point. Now I'm going to get into the redshift and why I don't feel it's accurate. But here's a good point, a quick note about the Hubble. So a question you may ask yourself: the Hubble telescope, can it take pictures of the Earth? Now here is a response. I'm going to put this on the screen. This is the response from Hubble and NASA of why, and the short answer is no, they can't. But I just wanted to put on the screen why they say they can't. You know, uh, they're basically saying that the Earth is moving too fast and that the exposure time is so short that the picture would be a streak. Okay, so my question is this: let's take a look at. I'm gonna go to. This is the latest video from the ISS. Okay, I'm just gonna play a little bit of this, and this is supposedly what you're looking at here is it was taken on July 2018, so this is pretty recent. And by the ISS, you're looking at Earth. This is so-called Earth from the ISS, which I think it's about 200 and something miles, supposedly, which will make it lower than the Hubble. But amazingly, it was able to take a picture. You know, these are so-called stitched pictures, compiled. They always have to compile or stitch something together. They never can just get a camera and freaking take a video. They have to stitch it together, have this weird processing going on. But anyway, that's just a side note. So the Hubble telescope amazingly can see, you know, 200 million light years away. But the guys didn't think, hey, what if we just kind of turn the camera around and took a little snapshot of Earth? You know, they didn't think of that. It's only designed to see distant objects. And when I say distance, I'm not talking about 50 feet. Excuse me, 50 miles. No, 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 no. We mean 50 million light years, buddy. We serious distance. And just think of that now. One light year is about 6 trillion miles. So you do the math on that. 6 trillion miles is enough for me to not even believe it can see that far. Seriously. Think about that in your head. Close your eyes and just even try to imagine 6 trillion miles. Try it. It's ridiculous. That's why you can't even think about it. Okay, so let's get into I'm gonna play a short clip kind of explaining what Redshift is, you know, for you guys who kind of technical. So this following clip is going to be uh, about 2 minutes.
Hubble and his assistant Milton Humason set about analyzing their spectra. The lines in a spectrum are what make it unique. They provide astrophysicists with a kind of optical fingerprint, which supplies various pieces of information. Among them, the chemical composition of the source, in this case, the galaxies. The two astronomers noticed that the lines were shifted towards the red end of the spectrum, a sign that the galaxies were moving away from the Earth. This red shift derives from the fact that the light is a wave. Visible light ranges from red, with a wavelength of about 700 nanometers, to violet, with a wavelength of 390 nanometers. Waves at the red end are longer. When a cosmic object, a galaxy for example, is receding from the Earth, the waves are stretched. In other words, its spectrum is shifted towards the red end. An approaching body would display a corresponding blue shift. Its waves would be squashed. This phenomenon, known as the Doppler effect, is also observable with sound. It is named after the Austrian physicist Christian Doppler, who noticed that a locomotive steam whistle sounds higher when it is approaching and lower when it's receding. The pitch changes because the sound waves and the sound source are moving. If the source is approaching, the waves are squashed and the shorter waves sound higher. If the train is moving away from us, the waves are stretched and longer waves sound lower. If this logic is applied to the galaxies, a redshift, in other words a lengthening of the light waves, means that the galaxy must be receding. Most of the galaxies investigated by Hubble were in fact redshifted, and the more distant they were, the more pronounced the red shift. This means that the most distant galaxies are receding the fastest.
Now let's go into a guy, another astronomer. He's pretty well known in the astronomy community, but obviously you've probably never heard of him. His name is Halton Arp. He's an astronomer. I'm going to put a picture of him on the screen here. Very well known. This guy's not a fluke here. Harvard educated. Got a bachelor's degree at Harvard. A PhD at Caltech. He was a member of the Max Planck Society. I mean, this guy has all kind of credentials. But the most important, one of the most important contributions I think he made was what he called, and you can look this up, it's called, and I'll put the link in the description, it is the Atlas of Peculiar Galaxies. And what this is evidence that he has put forth of anomalies, and it's about 300 galaxies that don't, you know, the redshift doesn't fit with these galaxies. Basically, these galaxies dispute redshift. So my question is this: before I even get into the guy, I'll let him explain it in a minute. I'll play a little interview here shortly. But what I'm getting at, before you even get into the interview and listen to the guy, it's not like he's providing one galaxy that Redshift didn't kind of work on. And you can go look it up. The guy has about, man, 300 galaxies. You can see on my screen to the left, if you go to that website, you can click on each one of those links, and they have several galaxies that are pure anomalies. So, really, just like the scientific method, if you find one, just one, that doesn't fit to the redshift theory, that should be enough. That should be, but he outdid himself. He provided about 300 at least. I think it's probably more than that. But anyway, let's get into the interview. Uh, Unfortunately, he has passed, but this interview was done in 1988. I want to say he passed in um, it was 2000 and something. I'm not sure, but he's not with us anymore. But this was an interview he did in 1988. Okay. Um, so take a listen to that, and I'll get back with you.
Look at this picture. Here we have the Virgo cluster of galaxies. And most of the smudges in that picture are not stars, but whole galaxies, each containing perhaps 100,000 million stars, and around about 50 million light years away. And that again is only the start. What about the quasars? The quasars, look at that little tiny dot there on the end of the arrow. That is a quasar. And according to conventional theory, it's superluminous, perhaps as luminous as 1,000 whole galaxies put together, and is more than 10,000 million light years away, and is receding at more than 90% of the velocity of light. Now, how do we tell that? And the answer is by using the spectroscope and the well-known Doppler effect. Remember, a spectroscope splits up light. And when you look at the spectrum of a star, or a galaxy, you see a rainbow background crossed by dark lines, each one of which is due to some particular element or group of elements. Now, if the light source is moving away, its light appears slightly too red. And that means that all the spectral lines are shifted over to the long wave or red end of the spectrum. That is the red shift, and it is absolutely vital because all our distance measures in the far universe depend upon it. Let's go back again to that quasar. Now, how do we know it is so remote and so luminous? Because of its red shift. The greater the red shift, the greater the distance, and the greater the velocity of recession. That's the conventional theory. But that depends upon the redshifts being pure Doppler effects. Now, just suppose there's some other cause of the redshift superimposed on the Doppler effect. And if that is so, if the redshifts are not pure Dopplers, then all our distance measures may be wrong. And one astronomer who believes that and has observational evidence to back it up is Dr. Halton Arp, formerly of the Mount Wilson Observatory and now of the Munich Institute. Dr. Arp, we're delighted to have you with us. If you're right, then the effects upon all our thinking are going to be pretty profound.
Our entire view of the universe, the size and the mass and the contents, depends on this assumption that we can tell distances by redshift. If that one crucial assumption is incorrect, then our picture falls apart and we don't know very much.
Well, first
Our entire view of the universe, the size and the mass and the contents, depends on this assumption that we can tell distances by redshift. If that one crucial assumption is incorrect, then our picture falls apart and we don't know very much.
Well, first of all, then, will you give us the observational evidence that you have that the redshifts are not pure Doppler effect or something else superimposed on it?
Fundamentally, the only way you can tell the distance in the universe is to see an object associated with another object whose distance you know. So that if you see objects which are clustered together or are interacting together, you know that they're at the same distance. And if you find that their redshifts are much different, then you know that the redshift can't be a measure of the distance. Now, an example of this we see in this very pretty spiral galaxy with 3 quasars on the edge of it. The quasars have enormously high redshift. and the spiral galaxy has a low redshift. These quasars are so close to the galaxy that they are statistically or probably associated. We see other examples of this. For example, here are 3 other quasars associated very, very close to a galaxy. Now, in addition to these close associations, which are statistically probable, we see quasars actually linked to the galaxy. In this case, the quasar Markarian 205, just below the disturbed galaxy NGC 4319, has a very much higher redshift than the galaxy, which is only about 2,000 kilometers per second. The quasar has about 21,000 kilometers per second. The next example shows a quasar of very high redshift, 1.17, and it's connected by a luminous bridge into a disturbed galaxy with a jet that you can see here. The galaxy is, again, very much lower redshift, and the quasar is a high redshift. Now, not only do we have these quasars of very high redshift linked and associated with lower redshift galaxies, but also we have galaxies themselves of different redshift, which are clearly interacting, but have much different redshift. This is a famous example of one of these. There are many like this known now. The central galaxy is a disturbed Seaford galaxy with a redshift of 8,000 kilometers per second, and the companion, which is linked to it, is 16,000 kilometers per second, much higher.
Now, are you sure these links are genuine? Could it be any kind of line of sight effect?
The only possibility is that there is an accidental projection of background objects. However, these objects fall so close that the probability is overwhelmingly that they are in fact associated. One of the objects we just saw, the chances was 1 in a million for an accidental association. Another object we just saw, the chances were 1 in 50,000. And there are many of these known.
In other words, there are too many of these cases to be explained away by line of sight effects or just coincidence.
That's right. Statistical investigations of complete samples have shown repeatedly that there are these significant associations. Moreover, they are characteristic of patterns in these associations which are repeated from association to association.
Well, that means, in fact, that the redshifts are not pure Doppler effects, and they're simply not reliable as indicators of distance.
That's right. The only observational test of this assumption that we have shows that the assumption is not correct.
Well, quite apart from that, what about these bridges? How exactly are they formed, and are there any distortions between various systems?
I think a good example is this NGC 4319 object, where you can actually see the luminous connection going from the center of the galaxy to the quasar Markarian 205.
What about the significance of the bridges, then?
Well, I think the significance is very central here, because the bridge goes back exactly to the center of the galaxy. That implies that the material was ejected from the center, and since it's an active nucleus, this makes good sense. Also, we must remember that it's accepted, and it's been proven, that the galaxies eject radio material, and they eject them in equal and opposite directions, so that it's very well accepted and believed that, in fact, as we see here, for instance, an active galaxy nucleus ejects these clouds of radio material, and in this particular case, there is a quasar associated very nearby. In another example, we see this typical radio galaxy ejecting radio material in either direction, and along the line of the ejection is a compact radio source, which in fact turns out to be a quasar of very high redshift. So that, in fact, we know that galaxies eject material, and the only point is what is being ejected. Now, we can see here, I think, one of the most spectacular examples of ejection. This is a spiral galaxy called NGC 1097, and this color picture shows the long, straight jets coming out from the center of this galaxy. In the next picture, which is a black and white, shows better the contrast in jets. You can actually see a faint fourth jet, again, always the ejection and the opposite ejection, showing luminous ejection of material from this galaxy. But now in this particular galaxy, it's very interesting because there are also radio and X-ray observations. The radio observations are shown here now on the black and white photo. The radio observations are shown in yellow, and they show that the radio material also goes along the line of these ejection of these jets. Finally, the X-ray observations are shown in blue. There are clouds of X-ray material around the nucleus of the active galaxy, obviously ejected from the galaxy, and obviously ejected in the direction of these jets, which are shown here in this picture. But now the really very important and impressive point is that in many of these clouds of X-ray materials, there is a point of light which turns out to be a quasar of very high redshift. These are marked by the X's. And these quasars of high redshift, therefore, are linked to the ejection in this galaxy because the radio material, the optical material, and the X-ray material are all ejected with these quasars.
What about the remarkable galaxy Messier 82 in the Great Bear?
M82 is a very well-known galaxy. It's a very strong radio source. It's a very strong infrared source. It's very disturbed. It's been known for a long time to be ejecting material. You can see it here in the picture. And accidentally, it was discovered that there were 4 quasars very nearby. These 4 quasars are indicated by these open circles, and it's very easy to draw this ejection cone back to the center of the active galaxy, and at the base of the ejection cone you see this little radio cloud. And most important of all, again, if you look at the X-ray observations in this galaxy, you see that the X-ray material is also coming out in this direction of these quasars.
Well, if quasars are being shot out from active galaxies, there might even be some in our local group, which is quite a thought. But now, what about galaxies themselves? Are there cases of galaxies which appear quite clearly to be associated and yet have totally different redshifts?
There are a large number of cases now where galaxies of quite different redshifts are seen to be interacting together, showing that they're at the same distance despite the fact that they have much different redshifts. A famous example of this, a much discussed example, is Stephan's quintet. Here you see the redder galaxies in the upper part of the picture have large redshifts, 5,700, 6,700 kilometers per second. And the blue galaxy in the lower part of the picture has a low redshift, only 900 kilometers per second. And yet you can see the interaction tail of the low galaxy due to the low galaxy interacting with the higher redshift galaxies. Now, something else is very interesting about this picture, and that is that these kinds of interacting galaxies typically occur in the outskirts, in the regions around big dominant galaxies, SB galaxies like our own M31 that dominate a group. So if you look a little ways away from Stephan's quintet, you in fact see this type of SB galaxy. It's called NGC 7331, and it looks just very similar to M31. Around that galaxy, you see other companions like Stephan's quintet, essentially the same redshift, 6,700 kilometers per second. They're obviously associated with 7331. It illustrates the kind of groups which make up space, which I think make up space, big dominant galaxies, and companions around them which have the slightly higher redshift and increasingly higher redshift, but are all located in the same region of space.
Again, you think there are too many of these to be put down to coincidence?
Yes, yes.
What about M31 and M81? They're 2 of our near spirals.
This follows the development of this investigation of groups of galaxies through to the most impressive point, I think. The M31 group and the M81 group are the 2 groups that we know the most about. The M31 group is our local group. We know all the companions in it. The M81 group is the next nearest group. We know all the companions there. This visual shows that the biggest galaxy in each group is the SB, M31, and M81. And now all the rest of the companions, which everyone has always accepted as being companions, have systematically higher redshift. The chance of 21 out of 21 companions being of accidentally all of higher redshift is only 1 in 2 million. But on the Doppler interpretation, we should have as many coming towards us as away from us, plus and minus. Clearly that's not the case, and clearly this is a point which is just inescapable. No future measures are going to change these redshifts, and we're not going to find any more companions, so we have to deal with this piece of evidence.
Well, you're certainly painting an entirely new picture. How do astronomers in general view it?
I think that, that there's a great commitment to the assumption that redshifts always mean velocity, and there's a great reluctance to give up this assumption because a lot of work has been based on it, and there is this reluctance to recognize evidence which contradicts this assumption. However, if it's true that the redshifts are not always indicative of velocity, And it's continued to be believed that it is, if this assumption is continued to be believed, then we reach a very critical point in the science of extragalactic astronomy. And this is so important that I think that everybody, every person then has to make up his own mind, exercise his own judgment on this matter, and therefore I think it's very important to discuss the facts of the matter as we have here.
I'm quite sure you're right there. Well, I'm no cosmologist, as you know. Anything beyond the orbit of Neptune is rather a long way out for me. But if you're right, and there is an extra redshift superimposed on the Doppler effect, what's the cause of this non-velocity redshift?
Well, the first point I have to make is that the observations show that the present assumptions are inadequate, so we have to have some other explanation. I think there are a number of explanations which are possible and which different people defend in a very spirited way. That's as it should be. My particular hypothesis, my working hypothesis, my explanation is that the matter which goes into making up these quasars and these higher redshift galaxies is young matter which has intrinsically high redshift, which is ejected from the galaxy and which decays and evolves as a function of time into more normal lower redshift galaxies.
Well, in general, it's generally thought that the high redshift galaxies are a long way away, and the high redshift quasars are the most distant, and therefore the most luminous. What you're saying is that instead of being the most luminous, the high redshift quasars are actually the least luminous.
That's the most exciting point for me. If the material out of which these newer quasars are formed has low mass, in the sense that the constituent particles, the electrons and the protons, have lower mass, then their redshift will be high. Now, there's a rigorous theory due to Fred Hoyle and Jean Narlikar that the mass of elementary particles, of the constituent particles, can evolve with time. My application of that to this situation is that it's the evolution with time of the mass of these particles which causes the initially high redshift to decay and become more normal.
In current physics, though, is this kind of creation of matter a possibility?
In past years, it has not been a very respectable thing to talk about creation of matter. And that's a little puzzling, really, because it's had a long and honorable history. The brilliant physicist Paul Dirac, more than a generation ago, talked about the creation of matter. Hoyle and Bondi and Gould talked about the creation of matter in connection with the steady state theory. Andrei Sakharov in 1965 suggested the creation of seeds of galaxy creation this way. So it has an honorable history. However, just recently it's become much more respectable because of inflation theory. Inflation theory is the attempt of physicists to explain the expanding universe by means of fundamental physics, and in that process they conceive of creation of matter. The technical term they use is fluctuations in the material vacuum. And essentially you're looking at a piece of space and the properties vary and suddenly some material appears. Well, why not? My hunch is that the material appears where material previously exists in the center nuclei of galaxies, and that then this material flows out along the bridges or perhaps along the spiral arms. And this particular spiral galaxy we see here, we see that there is a disturbance in the top, in the arm at the top, and if we look in more closely we find a very peculiar blue object associated with that spiral arm, and if we take the spectrum of that object we find amazingly that it has a redshift 1/10 the velocity of light, an enormous discrepancy. This reminds me of the remark that Sir James Jeans made more than a generation ago when he suggested that spiral galaxies perhaps were the place in our universe where matter was poured in from other universes.
Well, that's a kind of cyclic universe. Whether you're right or wrong remains to be seen, but it's a fascinating new picture, and of course it does stand or fall on the observational evidence. You presented a case, and now it's up to people to consider it and see what the evidence is. And I think we're going to have some very exciting developments in the near future. We're delighted to have you with us, and I hope you'll be back with us soon. So for the moment, from Dr. Arp and myself, good night.